All right, this fourth task, again, has a lot of jargon. Somehow or other, that just seems to happen when I write things up. But don't panic. It's really pretty simple. Basically, we have a number line. Here's 0. And on this number line, we can mark spots on it. And they could be anything. They could be 1, they could be a half. They could go out a little further. We get square root of 2, and so on and so forth. And there are just all these numbers on this number line. Now, we've seen that some of those numbers are what we call rational or fractions. And then there are these other numbers that we talked about a little while ago on that little sidetrack, if you did it, which I definitely encourage you to do. In any case, it's just a very reasonable explanation, right? We have this number line and it has numbers on it. And so we could mark some random point on that number line and ask, how close can we get to that random point with a rational number? So using a fraction, how close can we get? Now, if this is just a bit too abstract for students to get a hold of, go and put pi on that number line. Because if we put a rational number, automatically we're going to be able to hit the rational number by using a rational number. I mean, no kidding, Sherlock, a rational number is rational. But so suppose we just try some other number, namely pi, for a specific example. And you could say, okay, so let's move our line across. Here's 3, here's 4, here's pi. Most students sort of know that pi is about 3.14 something. It's a wonderful property that most students know about pi, even if they know nothing else about it. Heaven forbid. We will do an exploration on pi at some point, I promise. In any event, you can ask students, how close could we get to pi? And you might get blank looks. And if you get blank looks, say, well, could we get within 1 unit of pi? And at this stage, you really have to wait for an answer, because the reality is we could try 3 and 4, and we know that pi is somewhere between 3 and 4, so we're definitely within 1 unit of pi by choosing 3 and 4. Actually, by choosing 3 and 4, we've got to be within half a unit of pi, because pi couldn't sit between 3 and 4 and not be closer to one of the two, in which case it's got to be closer than halfway, so it's less than half. And then you can say, well, can we guarantee that we can get better than that? Some students might say, well, what about if we take 3.5, which we all know is 7/2. So now if we take 3.5, either pi sits between 3 and 3.5, or it sits between 3.5 and 4. Well, we actually know it sits between 3 and 3.5. But either way, this interval is length half, and that interval is length a half. And so pi has to be within a quarter of one of these 3 numbers. And all 3 of those numbers are rational. So pi has to be within a quarter of one of those numbers. Actually, we could do even better. I mean, well, let's just break up 3 to 4 into tenths. So you have 3, 3 and a tenth, 3 and 2 tenths, 3 and 3 tenths, 3 and 4 tenths, 3 and 5 tenths, and so on and so forth. And pi has to lie between 2 of those. Well, we actually know that it lies between 31/10 and 32/10, but that means that we've narrowed pi down to within a tenth. And there's nothing stopping us from now dividing it up into 100th or 1,000th. And the beautiful thing about this is we don't actually even need to know exactly where pi lies in the line. All we need to know is that we've divided it up into a whole lot of little intervals that are the same length. It's got to lie in between one of them. And so therefore, we can get as close as we want to pi with a rational number. Now, this is an existence proof. It doesn't actually give us a rational number that pi is within 1,000th of, but it tells us that such a number does exist. It's kind of cool. One of those crazy times in life where you know something exists, you can prove it exists, but you actually don't have an example of what that thing might be. Anyway, for the box version, we just do the same thing. Instead of cutting a number line up this way, we're now going to cut it up into a grid on the boxes. We divide the x's up into tenths or hundredths or thousandths, and we divide the y's up into tenths, hundredths or thousandths. And then each of the corners of all of those little squares are going to be made up of rational coordinates. And one of them's got to be within however close we want to get to the actual point. So we sort of box our way in. Fantastic, huh? And beautiful and visual.